62212 Lab 4 Magnetic Field of a Bar Magnet. The goal of this experiment was to investigate the distance dependence of a magnetic field of a small bar magnet using the Biot-Savart law and simulate the magnetic field of a bar magnet using VPython and comparing the measured magnetic fields to the simulated magnetic fields as well. The overall purpose of this experiment was to observe the impact of magnetic fields using compasses and using magnetometers to determine the directions and strengths of magnetic fields at various locations. The key physics concept involved in this lab was the Biot-Savart law, which relates the magnetic field in teslas from a source charge to the current of the source charge and the distance between the source charge and the observation point. For an infinitesimally small magnetic field for a section, it's equal to the equation below. In the far right field, where small r is much larger than big R, on the center axis of the loop of current, the magnetic field of the loop of current has the shape of the magnetic field of a dipole with the magnetic dipole moment mu, with the equations shown below. The direction of the on-axis magnetic field is the same direction as the magnetic dipole moment, i.e. it has the same direction as the conventional current I. Another key physics concept is the magnetic field of a dipole, where the magnetic field of the perpendicular magnetic field of a dipole is half of the parallel magnetic field. The direction of the perpendicular magnetic field is also opposite of the magnetic dipole moment, pointing in the parallel direction. And additionally, the magnitude of the magnetic field due to a bar magnet is the equation shown below, where K is equal to a combination of various magnetic constants, and we are given the general formula for the magnetic field of the magnetic dipole below. The initial conditions of our system and the key assumptions of our system include that our system is the observation point, i.e. where the magnetometer is placed, and the surroundings is the bar magnet which produces the magnetic field. We assume that we treat the bar magnet as a magnetic dipole, and we assume negligible effects from other forces and other effects. The overall procedure for this experiment involved getting our materials, which included a bar magnet, a magnetometer, meter sticks, a tape, and phones, and we compensate for the magnetic north by orienting the phone so that the x component shows 0. We then find the magnetometer chip in the phone with the described procedures, and we measure both the on-axis and the off-axis magnetic field with the procedures described below, where we measure the distance between the magnet and the magnetometer, where the magnetometer is on axis to the dipole axis of the magnet, where the x component of the magnetic field is equal to 20 teslas, 70 teslas, and all the way to 220 teslas. And we record the distance at each of these. For the off-axis magnetic field, we record the y component of the magnetic fields, where the net magnetic field is 100 teslas, and we apply this distance in the y direction to move the observation location to some distance 45 degrees out, and we measure magnetic field components at this location 3 times as well. Overall, we have this experimental data here where we fill in the yellow boxes and we get the graph on the right. Overall results were that the magnetic field of the net magnetic field, the magnitude of the net magnetic field increases as the separation distance decreases, i.e. an inverse relationship. The graph relates the natural logs of the net magnetic field to the magnetic constant of the bar magnet, where n is equal to the slope and the natural log of k is equal to the intercept. We then derive the magnetic dipole moment from equating constants to the dipole magnetic field equation as I described previously. And we correct the magnetic field in the y direction by subtracting Earth's magnetic field from the measured y component of the magnetic field. So overall, we find that the magnetic dipole moment is around 1.37, and the measured off-axis magnetic field is around 3.1 times 10 to the negative 5 teslas, while the simulated off-axis magnetic field distance is around 3.88 times 10 to the negative 5 teslas. For our computation model, this is our code. Pay attention to the definition of constants and magnetic field function, as well as the arrow scales and arrows for the magnetic field with the measured data. Here we define the constants mu 0 over pi, and as well as other various constants, such as the magnitude of the magnetic moment of the magnet. Here we create the function for the magnetic field, and below we find the observation axes, as well as arrows for various magnetic fields at various locations around the magnet. And at the very bottom, we visualize the magnetic field 45 degrees off axis. When I run the program, we receive this image. Some possible sources of error include other sources of magnetic fields distorting measurements, such as other electrical wires, devices, and electronic devices, as well as inconsistent placement of the smartphone, which leads to an inconsistent magnetic field measurements, as small shifts can lead to significant error. We also take note that the surface is not completely flat, and we may have measurement errors with the magnetometer and determining distances. What if we had not oriented your experiment to compensate for magnetic north and instead lay out your meter stick at some intermediate angle? Then the magnetic fields will be different since the magnetic north will affect the measurements. The x and y components would be different since the magnetic north contributes to the magnetic field measurements depending on the angle of the measurement. But since we lay the magnetic meter on a flat surface, the z component does not change, where there will be very little change, if any, observed. If we were to stick two identical magnets together and run the experiment again, then we would expect the magnitude of the magnetic field to increase since two magnets are combined together. Theoretically, the measurements would double due to the superposition principle, and measured distances for each magnetic field would decrease since the magnetic field magnitudes increase.